So now we are all set to apply the Schrödinger equation to one-dimensional systems. We will see that even relatively simple, stationary examples illustrate some of the most drastic and far-reaching implications of quantum mechanics for physical systems. Our goals for this section are the following. We will establish a quite general procedure to set up and solve quantum mechanical problems. Looking at the solutions, we will obtain concrete insights into the role of the energy and the wave function, the two parts that really make up the solution, not just for observations of energy and position, but indeed also for momentum, hence covering all the three central observables of such systems. As for our general procedure to set up and solve these problems, here is the general picture. The different physical situations simply differ in the form of the potential energy. This then enters the Schrödinger equation. And given that we are looking at the stationary variant, the solutions will be pairs of energies and wave functions. But the potential energy, of course, also exists in classical mechanics, and we will use this in two ways. For one, it helps us to motivate meaningful physical situations. But secondly, the physics encountered in the classical system will also provide valuable context to interpret the behavior of its quantum mechanical counterpart and alert us to effects which are special, hence identify genuine quantum effects. And there will be plenty of these, but even in the most drastic cases, we will often still find some traces of the classical behavior, and that will make these effects much more accessible to our understanding. And we have, of course, already exploited this in the motivation of the Schrödinger equation when we essentially looked at a free particle. Indeed, setting v to 0 in the Schrödinger equation, we see that the solutions are the momentum eigenstates psi p that are introduced in the previous segment. And moreover, the energy is related to the momentum eigenvalue in exactly the same way as for a classical free particle. What's more, to see this, we do indeed no longer need to apply calculus. We can use the simple algebraic fact that this is an eigenstate of p and apply this operator twice, which is indeed what we mean by the square of this operator. This shows that these notions not only help us with our interpretation of the solutions, here that energy and momentum are well defined in this state, but can indeed also simplify our calculations. So for this case, really our zeroth example, the energy looks quite classical, and the most obvious quantum effect is the fact that the particle can now be found anywhere in space, so is really extremely delocalized. But this observation exactly motivates our first proper example, namely to see what happens when we force a particle to be trapped somewhere in space. And we will see that this has far-reaching consequences, both for its energy and its momentum. So let's say the particle should be confined to this finite line segment in space. According to our general procedure to set up the problem, we next specify the potential, for which we can be guided by classical mechanics. There we can just say that the potential energy is so large outside the region that the particle never has enough energy to leave it. To be totally safe, we indeed take the limit that the potential energy is infinitely large outside the region of interest. We will revisit this assumption very soon, and we will see that it is actually important. What we have here is then what we call a hard wall. Later we will also look at soft walls, where the potential will still be finite. Inside the region, we just say the particle is free, hence V vanishes. The colloquial name for this problem is the particle in the box. You can also call it a particle in a square well. Let's try to formalize this. So V vanishes in the region of interest. Well, now we need to be specific and say that it's of length L and starts at the origin. And the potential is infinite elsewhere. I put here inverted commas. If you want to be cautious, just think of the corresponding limit. The next step is to write down the Schrödinger equation. This looks like the free particle between the walls and involves this very large potential inside the walls. So next we list the three main mathematical features that we need to adhere to, as introduced in the previous segment. This is the superposition principle, the continuity requirement on the wave function, and the boundary conditions. For the problem here, it is easiest to start with the last one, the boundary conditions. We look for solutions where the wave function drops to 0 at very large distances. But that's far inside the walls, where we better never find the particle. And indeed, mathematically, you can see that if the energy is finite on the left-hand side of the Schrödinger equation, then as the right-hand side needs to be finite too. For an infinitely large potential, this implies that psi vanishes, indeed everywhere within the walls. It is useful to overlay a sketch of the wave function on top of that of the potential. See the red line that I indicate there. Okay, so next let's look at the Schrödinger equation between the walls. This is the same as for the free particle, but now we need to be a bit more general than before. The energy only fixes the magnitude of the momentum, but not its direction. So we actually have to account for two versions of the plane wave, and according to the superposition principle, indeed all their possible combinations with two constants a and b. So between the walls we get some type of possibly complex oscillatory behavior, of which I sketch one component here, let's say the real part. This leaves one more condition, the continuity of the wave function. The only places where this isn't guaranteed is where the region ends and the walls start. Approaching these points from within the walls, we already know that the wave function vanishes, and so this must also be the case when we approach them from within the region. This gives us two algebraic conditions. Evaluating our solution at x equal to 0, the left boundary of the region, we find that the coefficients a and b must sum to 0. Note that the exponential function is 1 when the exponent vanishes, so we can actually set b to minus a. Using the Euler identity, we can rewrite this as a sine function, which indeed nicely vanishes at the origin, and the coefficient in front we can replace by a new constant, little a, just to keep everything simple. Now we apply the same logic to the other end of the region at x equals to L. This gives us a different condition. A times the sine function must vanish at this point. But we cannot set a to 0. The wave function would then really vanish everywhere, including between the walls. So we cannot use this to calculate probabilities and have to rule this out as a physical quantum state of the particle. You may be tempted to think of this as a quantum state with no particle, but that's actually more involved and not what we are interested in here. So our only choice is to make use of the places where the sine function vanishes, its so-called nodes which appear at multiples of pi. Looking at the argument of the sine function, we can write this as a condition for k, which is really the quantity which we have not determined yet. The length of the region is given. Now in here n are positive integers that enumerate nodes of the sine function. We cannot allow for n equals to 0. This just gives us a wave function which vanishes everywhere. And we do not account for the negative integers separately, because this just gives us the same solutions with a minus sign. But since our solutions still contain the arbitrary constant a, this does not give us anything new. This exhausts all our mathematical conditions. In particular, we do not need to require that the derivative of the wave function is continuous as well. If you look at the sketch above, the wave function indeed does have a kink at the boundaries of the region where the potential energy becomes infinitely large. Just as a small remark, you may wonder if you could have stipulated the boundary conditions at the end of the region directly. But our reasoning was based on the fact that we would like to get finite probabilities out of the solution, and in a finite region this could also be obtained even when the wave function does not vanish at such places. Indeed, when we disregard how the region is terminated physically, it may really be representing positions, say, around a ring, so that when you leave it on one side, you re-enter it on the other. And you can build such rings in the semiconductor heterostructure. That would be a related problem, really a very interesting one, but with somewhat different solutions. Right, so let us collect our results for this problem here and then try to make sense of them. The wave function is a sine function between the walls, with nodes exactly where this region ends. And there it connects smoothly to the vanishing solutions inside the walls. And we can now also write down the energy. You could read this off by inserting the solutions into the Schrödinger equation, but even simpler, we can again do this algebraically by translating the wave numbers first to the momentum and then to the energy. So now to get a feeling of what this all means, let us compare the classical and quantum variants of this problem. On the classical side, we can give the particle any positive energy. It will then move ballistically between the walls. Its momentum remains fixed into a certain direction until it hits the wall, where it then becomes reflected, and this motion just continues periodically. The energy could also vanish. The classical particle then just sits at some position between the walls, not moving at all. But on the quantum side, we only ended up with very specific energies, discrete values, which we call energy levels. They can be enumerated by an index, such as here by the positive integer n. This phenomenon, that these values are discrete, we call energy quantization. Let me mention that the word quantization actually has many different meanings. For instance, the procedure to pass from classical to quantum problems is also called quantization, but the specific term energy quantization always means exactly what we see here. And to further fix our notions, the lowest energy level that we can find we call the ground state, and the other states we call the excited states. As it turns out, even in the ground state, at its lowest possible energy, the quantum system has a finite energy. This too is a very general observation. Quantum systems cannot attain energies as low as their classical counterparts. This was indeed a very important realization already in the early development of the theory. Classical potentials can also allow infinitely negative energies, as in the Coulomb potential, but that would make such systems unstable if they could just release this energy to the outside. And as we will see later when we study the hydrogen atom, this problem simply does not occur in the quantum mechanical description. One way to think of this finite energy is to say that the particle cannot just sit somewhere at a fixed place in this finite region. It will always have some finite kinetic energy, hence generally some finite momentum. And that's indeed a very useful way to think about this feature, which we will soon develop into a precise statement, the Heisenberg uncertainty principle. Looking at our expressions above, it is tempting to think that momentum here is also quantized, but that's actually not the case, as I'll soon explain. But before discussing the momentum, let's first look at position. As introduced before, the idea is to take the mathematical solutions of the Schrödinger equation, these wave functions here, and translate them into a probability density. So let me first and finally explain what a probability density really is. It is actually quite simple. Say you would like to know what the probability is to find the particle in a certain region in space, really any arbitrary region in any kind of one-dimensional problem, but for instance between 2 points x1 and x2. You can determine this by looking at very small subregions and then sum the results up. Now taking the limit where the subregions become vanishingly small, this defines an integral, and the integrand we call the probability density. So the actual probabilities are the sizes of certain areas under the density, such as indicated here. Now if we add up all probabilities, hence look everywhere in space, we need to get 1. The particle needs to be somewhere, and we can write this as an integral over the probability density. So, given our premise that the probability density should be given by the absolute value squared of the wave function, we get this corresponding integral involving psi, which is an additional condition for the wave function. We call this the normalization condition. Indeed, we mentioned this condition already before when we motivated the boundary conditions. But so far we have not exploited it fully because this integral now needs to give us this very specific value. Fortunately, the boundary conditions are enough to guarantee us that we will be fine. We now just have to select an appropriate value for the free coefficient in front of the wave function, which determines its overall amplitude. In the solutions above, this is simply a, but a similar coefficient will always appear in our problems simply because the Schrödinger equation is linear, so any solution comes along with an arbitrary constant factor. And given that this definition of the probability density here can also never be negative, we have covered all the important requirements to interpret the wave function in these probabilistic terms. So let us complete this part of the problem by determining a suitable value for A. We need to take the absolute value squared of our solutions and integrate over all space, but then only pick up finite values from the region where the wave function is finite. So here we actually get an integral over a finite region. And inserting the solution, we basically need to integrate over the square of a sine function between two positions where the sine function vanishes. But we get very symmetrical oscillations in this case. Indeed, these oscillations are quite famously exactly 1/2 in height on average. You can check this by using trigonometric identities to convert this into a simple offset sine integral. But the steps are not essential. It simply means that the integral can be evaluated exactly and gives us 1/2 times the length of the interval L. This gives us a condition for A, and we've been careful here. Note that this only determines the absolute value of A, but we are fine to just take the simplest choice as indicated here. So this determines the normalized wave function, and from this we can then find the probability density. I here write this down only for the region where these quantities are indeed finite. Just for comfort, for this probability density, it really does not matter which complex number we have taken for A, as long as it has the right absolute value. All choices are covered if we would include an arbitrary complex phase factor, as it simply drops out when we take the absolute value square of the wave function. And just as an aside, this allows us to an interesting fact. It's not the wave function itself that determines the physical consequences. We are really interested in the probabilities. And this line of thought can be pursued to argue that the wave function itself, including this phase factor, cannot be determined in physical measurements. But that's actually not so uncommon in physics. Think, for instance, of electromagnetism, where it is convenient to work with the scalar and vector potential instead of the physical electric and magnetic fields. And just as the gauge freedom that one then encounters there, what we have seen here gives us some deeper insights into the true nature of quantum mechanics. Indeed, as it turns out, this freedom of choice in both theories is related, and it's important to write down fundamental quantum theories where particles interact with such fields. Okay, so now that we have our normalized wave functions, we better look at some sketches. Here I show you the first two states, the ground state and the first excited state. Interestingly, the excited states all have places inside the region where they vanish. We call these places nodes, also in other problems where they do not come from a sine function. When we square the wave functions, we get the corresponding probability densities, which again display these symmetric oscillations that we already mentioned when we worked out the normalization integral. So they look a bit like a diffraction pattern and tell us where we are likely to find the particle in space. Recall the discussion of the double slit experiment. Starting from particles of fixed energy, each position measurement would look like a random event, but collecting enough of them we can build up a histogram, and that would then look like one of these densities. So we conclude that the particle is still delocalized in space, but of course overall confined to the region between the walls, which was what we set out to achieve at the beginning. But in our original motivation, we also refer to the question what then happens with the momentum. This can be answered on two levels, and both give interesting insights. First, note that we had to make use of both counterpropagating waves to find the correct solution. What we have here is a typical standing wave pattern formed by counterpropagating waves of equal amplitude. And indeed, if we would do a measurement that just detects whether the particle moves to the right or to the left, we would find random outcomes with equal probabilities for both cases. But as I indicated before, if we measure the value of momentum, we will not just find two specific opposite values. Momentum is not exactly quantized in this case. The reason for this isn't that deep. After all, a state of fixed momentum is a plane wave throughout all space, and here we look at a truncated version. And it is exactly this reasoning that helps us to write down the more precise answer and determine the exact probability density for measurements concerning momentum, not position, and this is what we will do in the next segment.